Okay, so now we have these two equations, right? The left-hand side and the right-hand side of this equation. So if we equal these two, we see the only way this can be equal to that one is these two. If for these two, is that m to m1 to be 1, right? So equality of the RHS of the LHS left hand side and RHS leads to Fm equals to 1, right? So this is the first finding we have. And how about the other coefficients? So let's investigate them. So I want to start with Fm. So Fm, the definition, if you remember, is this, right? So I'm going to just write it down. Fm is sigma j equals to P1 to P2 of gamma j xj minus x star to power m over m factorial, right? And we said this equals to 1, right? Okay. So I want to just make an approximation for simplicity. Let's say Fm is approximately sigma gamma j, and instead of xj minus x star, I'm just going to write delta x to power m over m factorial, which equals to 1. And this is going to tell me that this only holds only if gamma j is approximately equal, is scaled with 1 over delta x to power m, right? So if you multiply this by delta x over delta x to power m, and then you sum them up, you can obtain 1, right? So this should be the scale of gamma j with respect to delta x, right? Okay, so now that we have this, let's do this. Given gamma j is on the order of 1 over delta x to power m, consider f0, f1 up to fm minus 1. Okay, so let's go to f1. F0. F0 is what? Is just the sigma of gamma j's. So F0 is gonna be sigma gamma j, which scales with based on this, scales with delta x to power minus m, right? Okay, so now what I'm going to use? I'm going to use consistency requirements. So let's see. For consistency, so I'm going to use consistency requirements of finite difference methods. Okay, so for consistency requirements mentions as delta x goes to 0, okay, my truncation error should also go to 0. Okay, but the thing is, as delta x goes to 0, okay, so let me write it this way. So the consistency requirement says limit of, and let me see if I have it here. Yes. It says the limit of, I think I had it before. Let me see. Yeah, the limit of the truncation error as delta x goes to 0 should be 0, right? So this is a consistency requirement. So the limit of the truncation error should go to 0 as delta x goes to 0. Okay, so let's see. This is a so this means here as delta x, but here as delta x goes to 0, you see that this sigma gamma j goes to what? Infinity, right? Because delta x goes to 0, so then 1 over delta x is going to go to infinity, right? So sigma j is going to go to infinity. So this means the only way that consistency requirement can hold is if this f0 is what? Is 0. Right? So the only way this holds is that all these gammas are going to cancel out. So this means like gamma 1 plus gamma 2, gamma p1, let me write it this way because we had it there, gamma p1 plus gamma p1 plus 1 up to gamma p2, they all equal to 0, right? So this is the only way that this can hold, okay? So we found the second thing. So the second coefficient. So let's do the next one. The next one is f1, which is what? Which is sigma gamma j times xj minus x star. So it's going to be sigma gamma j xj minus x star. And this scales with what? Gamma j scales with 1 over delta x to the power m, right? And then we have the second term, which we, for simplicity, write it as delta x. So this scales with, the whole thing scales with delta x to power minus m plus 1, right? Okay. So again, for this term, we can apply consistency requirement again, and this will lead to the same conclusion that f2, f1 should also be 0. The only way that consistency requirement can hold is if also f1 is 0. So we go on and on with this, and all the other coefficients except fm is gonna be also 0 because they are scaling with delta x over a negative number. So let's look at the fm minus 1 as the last one. So this one is gonna also give me based on these, similarly, it's gonna be 0, right? So fm minus 1 is gonna be also similarly 0 because it scales with delta x over to the power minus 1. Okay, so we can say that consistency leads to consistency requirement leads to F1 F0 equals to F1 equals to F2 equals to Fm minus 1 equals to 0, and Fm equals to 1. Okay, so based on consistency, we were able to find these coefficients of these finite difference approximation, this general finite difference approximation that we made. Okay, so now I want to convert these, and we want to find these gammas, right? So in order to do that, I'm gonna create a matrix. Okay, so I'm gonna make a matrix for these. So make a matrix representation. Okay, so let's do that. I'm gonna show it with this. Let me do it with this color. To here. Here. And here. Okay. Okay, so let's see. So this is a matrix, just so you know. This is a matrix. Okay, so the first term, so here I'm gonna write these equations, right? So F0 is just sigma gamma j, and then I have the other one, sigma gamma j times x j minus x star, another term. So the variables that the unknowns here are gamma j's, right? So I have here gamma p1, the first term. Second term is gamma p2, second one is gamma p1 plus 1. And this list goes on and on until gamma p2, right? Okay, so the first equation is just F0, which is this equation, right? So gamma p1 plus 1 plus etc. up to gamma p2 equals to 0. So I have this. I'm going to have 1 here, then 1 here, and then this goes on and on until the last one equals to 0. So this is the first equation I have. So the second equation is F1 is 0. So F1 is what? It is this. So it's sigma gamma j times xj minus x star. So I'm going to have what? So the second one is this term, right? xj minus x star right? So what I'm gonna have is, if you write this down, is gonna be, okay, so it's gonna be xp1 minus x star, and then the second term is gonna be xp1 plus 1 minus x star, and this list goes on and on until the last one, which is xp2 minus x star, right? Because this is xj minus x star, right? Let me see. Yes, it is xj minus x star, right? Times gamma j. So this is the way it's gonna go, and this goes on and on until the last one, the last term is gonna be xp1 minus x star to power m to power, let me see, yeah, the last one is this one, right? fm. So it's going to be power m over m factorial. So it's going to be power m over m factorial. The next term is going to be similar to that until the last one, which is going to be xp2 minus x star to power m over m factorial. Okay. So this one is again 0, and all these terms are also 0 except the last one. So the last one is actually fm equals to 1, right? So this is, if I want to write it, this is fm equals to 1 equation. This is f0 equals to 0 equation. This is f1 equals to 0 equation, okay? So this is a matrix that we obtain, okay? So I'm gonna write this as, name this as A, matrix A, which has a dimension of m plus 1 times p, right? So it has p rows and m plus 1 columns. Let me just double check it. Sorry, it has m plus 1 column, m plus 1 rows here, and p rows here. Okay, so this is why we have it m plus 1 times p. And then the second one is gamma, which has p rows and 1 column, right? And this one is going to be what? Is going to be, the dimension of it is going to be what? Is going to be m plus 1 times 1, right? When you multiply these two matrices, you are going to get that. You are going to get m plus 1 times 1, because it's m plus 1 times p, then time it multiplied by p times 1, you're going to get m plus 1 times 1, right? Okay. So now we are going to have 3 scenarios for the solution of gamma j's, okay? Based on those scenarios, we can have different solutions and different ways of solving this matrix. So we have to solve this matrix form to get these gamma j's, which are our unknowns, right? So these are the unknowns. We don't know them. And we want to find as a general approximation for these finite difference method. any finite difference method that we have, okay? So the conditions or cases that we are going to have here are as this. So the first case is case 1. M plus 1 is M plus 1 equals to P. What does this mean? This means that the number of points that we are going to take to make a finite difference approximation is exactly one number more than the order of the derivative. For example, if your derivative is first, or your derivative, you are doing approximating a first derivative, like when m equals to 1, this means the number of points that I am going to use to approximate that is going to be 2. So I want to, this means, for example, if I have anything like this, a curve, and then I wanna say calculate the or approximate the first order derivative, or the first order derivative of this function, okay, like, which is going to be this, I'm going to just use 2 points. So I'm going to use this point and another point, for example, here, okay, and then approximate this as this, okay. So this means that. Or if you are using a second order, like if you want to calculate the second derivative, then you are going to use 3 points. So just the number, just the degree of your derivative that you are taking, and plus 1. And the number of points that you are going to use is the degree of derivative that you have plus 1. Okay, so this is the first case, just to give you what does this mean. Then we are going to have a square matrix, right? As you can see here. So this matrix is going to be a square because m plus 1 equals to p. So in this situation or condition, the determinant of A is called Vandermonde determinant, which is guaranteed to be non-zero. Okay, so this means the determinant of A is gonna be non-zero, and therefore solution for the set of gamma j's is gonna be unique. So this means if your number of points that you want to approximate a derivative is just 1 point more than the order of the derivative. So if it is, for example, second order, or you want to approximate it with 3 points, you are going to have a unique solution in this matrix, which is only for first order approximations. Just note that, because here we didn't talk about higher orders, like we didn't try to set, for example, delta x to the power m plus 1 and other ones to 0. So you're going to have a unique solution in this way if your number of points is just 1 higher than the order of the derivative. Okay, So let's investigate the other condition. So the other condition that we might have is case 2, that your number of points is smaller than n plus 1. So for example, maybe let me write it this way so it's easier for you to comprehend what I mean. So the number of points is smaller than n plus 1, the number of points that you want to approximate. So this means, for example, say you want to approximate a first order derivative like du over dx, where m is 1 here, right? With just 1 point, right? And this is smaller than 1 plus 1. Is it possible? It doesn't seem possible, right? It doesn't seem possible that you can approximate du over dx with just 1 point. Okay. So this can be mathematically shown, and I'm not going to go through the details, but we can show that the rank of, from your algebra, you can show that the rank of A and B is not gonna equal to rank of A, and so there is no solution for gamma j's in this condition. Okay. Sorry about this. So there is no solution for gamma j's in this condition. And then we have the third condition. So the third condition is case 3, is when your number of points is greater than the order of the derivative plus 1. So for example, you want to approximate du over dx in which m equals to 1 with instead of 2 points, you want to approximate it with 3 points. All right? So what happens in these conditions? It is possible. Of course, it is possible to do that, but it has a caveat. So in this condition, the rank of A and B is gonna equal to rank of A, and so we are gonna have infinitely many solutions for gamma j. So if your number of points are greater than the order plus 1, you are going to have many solutions. You can have a lot of approximations, different approximations for that. And the only when you are going to have a unique solution if your number of points is just m plus 1, your order of derivative plus 1. Okay, so in the next lecture, I'm gonna go to more details of this, and I'm gonna solve one example exactly how you can find any general kind of finite difference approximation based on this method. And there are also other ways, like you can just use Taylor series, but this is kind of a generalization for any type of finite difference method that you can find and use. Okay. So let's have a brief review of what we learned today. So we started with the general formulation for finite difference approximations. And we showed that all the finite difference approximations are of the form of this, which is a number of a grid point multiplied by value of the that function or that variable in a grid point multiplied by a coefficient. And then the question became how to choose and how to find these gamma j's, these coefficients. So this was the whole question of this lecture that we addressed. So we started to write this expand this sum, okay, as here, and said we suppose we have only p points that we want to approximate these derivative with those p points. And then consistency requirement, we just wrote that based on the consistency requirement, this Taylor truncation error should be 0 as delta x goes to 0. So this means that r should be greater than 0 in this here. And then we substitute the Taylor series for each uj inside this sum. And what we found is, what we got is this sum here. And then we just factored out u star, the derivative, the first derivative, second derivative, and the mth derivative of that. And then we got some coefficients, f0, f1, f2, and fm, which are multiplied by those. Okay. And then we wrote this, the sum here, equaled it to the right-hand side here. And when you do that, you are going to get this. And this equality of the left-hand side and right-hand side of this equation shows that fm should be 1, so that these two terms are going to be equal to each other. And so based on this, we approximated the gamma j. The scale of that is going to be 1 over delta x or to power m. And then we substitute this finding into other coefficients, f naught, and we found that delta x, for example, for f naught, it's gonna scale as delta x to the power minus m. And so as delta x goes to 0, in order for it to go to 0, the only way it can happen is if f0 is 0. So all of them have to, the sum of all the gamma j's have to become 0, right? So similarly, we found it for f1, which is going to scale as delta x to the power minus m plus 1. So f1 also should be 0. And this goes on and on until fm minus 1, right? So fm minus 1 should also be 0. So based on consistency, we had this, and we converted all these equations into a matrix. So we made a matrix representation of that for all these equations that we found. And this is the matrix representation. And based on this matrix, we have to solve this matrix in order to be able to find all the gammas, right? All the gamma j's, the coefficients for those approximations. And then we had 3 cases. One is if m plus 1 equals to p, which we are going to have a square matrix. And then in this case, we are going to have a unique solution for gamma j's. The second case is when the number of points is smaller than the order of the derivative plus 1, there we are not going to have any solution for this type. We are not going to have any final difference approximation for this condition. And the third case is when the number of points is greater than the order of the derivative plus 1. And in this case, we are going to have many or infinite solutions for gamma j's. Okay, so in the next lecture, we are going to go to more details of this, and we are going to solve one example for finite difference approximation. And after that, after these are done, we are going to talk about time marching methods. Okay, thank you very much, everyone.